This topic is about the product and quotients of functions. You will have done products earlier, and so part of this will be a review. And you have worked with quotients, but we haven't specifically talked about quotients. In here, you will also be looking at a variety of functions that you will be combining together. So in the mind's on, I would just like you to take a moment to consider what the domain of f times g at x would be given these two functions, f at x and g at x. What I want to remind you is that when you combine functions, their domains have to overlap. So we need to look at where the domain of f at x overlaps with the domain of g at x. So I'd like you to take a moment to consider that, pause the video, and see what you can come up with. So in order to do this, what we want to do is take a look at each function separately and determine what their domains are. So looking at f at x, we know that because it's a square root function, that what's under the square root needs to be 0 or greater. It can't be a negative. That means that x minus 3 must be greater than or equal to 0. Solving that, x must be greater than or equal to, bring this minus 3 over and change the sign, or add 3 to both sides. So x must be greater than or equal to 3. For g at x, it's also a square root function, but in this case, we have minus x plus 3, which must be greater than or equal to 0. Dividing both sides by -1 means we have to switch the sign, and we would end up with x plus 3 is less than or equal to 0. Bringing this 3 over and changing its sign, we end up with x is less than or equal to -3. So the domain for this function is the set of x is an element of R such that x is less than or equal to -3. The domain for this first function is the set of x is an element of R such that x is greater than or equal to 3. So if you look at these two domains, you'll notice that these two don't overlap at all. So as a result, these two functions can't be combined. Therefore, the domain of f at x times g at x is an empty set because there's no overlap and these two functions can't be combined. Now what I'd like you to do is look at these two sets, which is given in terms of set notation, so you actually have the points for each set. And remember, in order to combine these in either case, multiplying or dividing them, a product or a quotient, they need to have overlapping domains. So what I'd like you to do right now is go through and circle the points in each set that overlap with each other. So what we have are these 2 points. These two both have a domain or an x value of -1. These 2 points both have x as 1, so they have the same input. And then these 2 points go together. So both of these functions can be combined for these points here where they share the same x values. When we solve them, recall that the input remains the same. So for the input of -9, we end up with 5 times -1, which is -5. For the input of -1, we are multiplying 3 times 10, which is 30. For the input of 1, we're multiplying -9 times 10, which is -90. And for the input of 5, we're multiplying minus 8 times minus 20, which is positive 160. So that is the answer to the first question. The second question, g at x divided by f at x. Again, the inputs will be the same. So for minus 9, what we have is minus 1 divided by 5, which is minus 1/5. For the input of minus 1, we have 10 divided by 3, so that is 10 over 3. For the input of 1, we have minus 9 divided by 10. That gives us minus 9/10. And for the input of 5, we have minus 20 divided by 8. We can reduce that. 4 will go into each of these, so it's going to be positive because same sign positive. 4 goes into 20 5 times, which is in the numerator. And then 4 goes into 8 2 times. Now we're going to look at combining these functions algebraically. In this example, we have two functions, f at x and g at x, and we're going to be finding their product. There's a few things I want you to be keeping in mind and that we want to be aware of as we go through. Once again, one of the keys is the domain, because of the fact that the domains have to overlap. So the first item will be to write the domain for each separate function. Then we're going to determine the domain for the combined function. We're going to find the equation of the combined function algebraically. And finally, we're going to graph it using Desmos so we get a sense of what it looks like. Looking at the domains of each function, starting with f at x, the domain is equal to the set of x is an element of R because it's a parabola, it's quadratic. And we know that with quadratics, you can put any number in for x without having any kind of a problem. There will be no errors that we will have to deal with. Looking at g at x, it's similar. It's linear, and it also has a domain of x element of R. Because they're both x element of R, these can be combined completely over their entire domain. And so now what we want to do is look at the domain of the combined function, and we can see that that's also going to be x element of R. So domain is equal to the set of x is an element of R. C now asks us to find the equation of f times g at x. So this equals f at x is 2x squared. G at x is 3x plus 2. Multiplying the two together, 2 times 3 is 6. X squared times x gives us x cubed plus 4x squared. And now that's our new combined function. And as you can see, knowing what you know about cubic functions, we're also aware of the fact that a cubic function has a domain of x element of R, which matches with what we determined over here. And so the last step is we just want to see this function graphically. And we've done lots of graphing in the past. What we're going to do is simply use Desmos to graph it. So we'll go to Desmos and graph this function, and then I'm going to paste it into here. The combined function was 6x cubed plus 4x squared. And this should look familiar because we've graphed these kinds of functions before. So here it is, and we're going to take that and I'm going to paste it into the document that I have. So the goal of this is to be able to anticipate what kind of function you're going to have when you finish combining them, and be able to have a sense of what it would look like based on how it's being combined, have a sense of its domain, and possibly an idea of what its range is. So here's my graph here, and this matches with what we have said along the way, that the domain of this function is an x element of R. And we can see from the combination here that it's a cubic function. It would be a good idea to do this next function example on your own, where you're combining them through division, and then come back and see how you did. So once again, we're going through all of the same steps. We want to write the domain of each individual function, determine the domain of the combined function, find the equation, and then graph it in Desmos just to make sure we have a sense of what it looks like. And there's going to be some functions, and this is an example of it, where we haven't worked with combining these kind. And so you'll have to do your best to become familiar with the different ways of combining functions and trying to anticipate what they would look like. Looking at the domain of each of these, for f at x, it's quadratic. So once again, its domain is x element of R. For g at x, we reviewed square root functions in the minds on. The value underneath the root sign has to be greater than or equal to 0 so that we don't have the square root of a negative. So the domain would be equal to the set of, and I'm going to do a calculation just up here, x plus 3 must be greater than or equal to 0. Bringing this to the other side, x must be greater than or equal to negative 3. So our domain is x element of R such that x is greater than or equal to negative 3. Now in this case, we do see that because the domain here is x element of R, that these certainly do overlap, and that it's really this function here that's going to constrain the domain for the entire combined function. Now looking at B, thinking about the combined function, first of all, I just noted that this is going to be a determining factor here, so that our domain is at least going to be x greater than or equal to negative 3. Now for this, I do need to think ahead to the fact that these two are being divided. This function is going to be in the numerator, and it's divided by g at x, so this will be in the denominator. Now that brings me to another point that I have to consider. I don't want division by 0. And we know that when this is equal to minus 3, it ends up being equal to 0. And that would give us division by 0. So because of the nature of this function, we're going to have to limit this to x greater than negative 3. So the domain of f divided by g at x would be equal to the set of x is an element of R such that x is greater than negative 3. Next step is to actually combine these. F divided by g at x, or f at x divided by g at x, is equal to 0.5x squared plus 1 all over the square root of x plus 3. Now at this point, what we have to remember is our math conventions. We cannot leave anything that would lead to a decimal value in the denominator. And so even when it's in variable form and we don't actually have any values, we want to rationalize this denominator. So we need to multiply the denominator by x plus 3, the square root of it, and the same to the numerator, square root of x plus 3. What this results in is 0.5 x squared times the square root of x plus 3, and its distribution, so I'm actually going to add some brackets in here just to make that clear, plus the square root of x plus 3, all over x plus 3. And then we would look it over to see if there's any more simplifying we can do. I recognize that it looks kind of messy, but that's what happens when you start combining a variety of functions, and really this is just the beginning. If you go on to math beyond this level, there comes a time when there's that many more functions as we're trying to model what goes on in the world, and the functions will be endless variety. Now we have our combined function. What we want to do then is see the graph of it, and as you can imagine, this is not something that we have practice in graphing. So this is where something like Desmos is very helpful. So we're going to go and graph this in Desmos and get a sense of what it looks like. Now, before we go there, it is good for you to take a moment to consider what you might think it looks like. And one thing is that we have dealt with quotient functions. So knowing that down here, we can get 0 for x equals minus 3, that would imply that we're going to have an asymptote. So I would expect an asymptote in this function at x equals minus 3. Beyond that, these values here partly are square root functions, so there's going to be some limit here, which we've already adhered to in terms of our domain. So we know the values are minus 3 and greater. What we can do is just reason out as we put numbers greater than minus 3 in here. So imagine 0 and 5 and 6 and 10 and 100 and a million. These values are all just going to keep getting bigger. So what we can expect is, besides having an asymptote, that this function is going to continue to grow because of a couple of things. One, the exponent, when we combine these, this is to the half. Remember, roots are the same as an exponent to a half, times 2. So we would add those together. That would be 2.5. So this exponent in general is greater than this one. So this will should go to infinity at its end, in terms of its end behaviors. So let's go ahead and graph this in Desmos and see what it looks like. Our new equation is y equals 0.5x squared, and that's times the square root of x plus 3. And that is plus, again, the square root of x plus 3. And all of that is divided by x plus 3. And so you can see here that we have what we anticipated. We have an asymptote at x equals minus 3 vertically. And then you'll notice that the end behaviors of this function are going to infinity, and that our domain is correct. So I'm going to paste this into my document. Pasting this in. And so as we have done here, what I would like you to see you do when you're doing your practice is to be anticipating what these graphs are going to look like as you work through these and figure out the domain and combine the functions. At this point, you want to be able to have an idea of what this graph could look like. And a good way of checking that understanding would be to have questions where you combine a function and then there are graphs from you to pick from, and you would have to pick which graph that the function goes with. So you can go ahead and complete the practice that goes with this work.